guys, it's me again. I'm going to do your overviews for topics 4, 5, and 6. This one's going to be topic 4. Let's get started. Okay, so this topic is equation writing. So I tried to type it out because it seemed like my handwriting wasn't scanning very well. So we're going to do summary of types of reactions and formatting, and then harder reactions that you might see. Okay, so first one, double replacement. So the format is AB plus CD, innies and outies combine. So you get AD plus CB. Remember, C needs to go first because it's positive. Do you need net ionics for doubles? Yes, you do. So when they say, if you're doing the equation writing section, you're lucky enough to get a double replacement reaction, automatically go right into your net ionics. Okay, synthesis. We have A plus B yields AB. So for this, just look for two elements combining. When you combine them, make sure to look up their charges and cross them. Another type of synthesis is when you have a metal oxide plus a non-metal oxide makes a salt. And in this format, you'll have metal comes first, non-metal, and then oxygen. And for these, you can literally just add them together. Net ionic? No. Alright, decomposition. We have a simple binary compound, AB, is going to yield A plus B. A metal carbonate is going to make a metal oxide plus CO2. It's like whatever is left over. A metal hydrogen carbonate is going to make a metal oxide plus H2O plus CO2. Metal hydroxide is going to make a metal oxide plus H2O. A metal chlorate is going to make a metal chloride plus O2. And then an oxyacid is an acid that has oxygen in it. Obviously, it's going to start with an H. And it'll be a weak acid, like, for example, H2CO3 or H3PO4. You're going to get a non-metal oxide plus water. Salt with oxygen is the opposite of this one. So you're going to make a metal oxide plus your non-metal oxide. No net ionics. Okay, single replacement. This one seemed to be tricky for you guys. So A and B, this is general format, are going to switch spots to get AC plus B, unless you have a halogen, in which case, if this were a halogen and C were a halogen, they would switch spots. You do need net ionics for singles. Alright, combustion. We have a hydrocarbon plus O2 is going to make CO2 plus water. Your metal or non-metal sulfide plus O2 is going to make a metal or non-metal oxide plus SO2. No net for these. And then water is a reactant. Metal or metal hydride plus H2O is going to give you a base plus H2. Remember, bases end in OH. Metal oxide plus water is going to give you a base. Non-metal oxide plus water is going to give you an acid. These you need net ionics on the product side only. Okay, so things that dissociate. These are going to be any soluble salts, Look at that, you need to remember your solubility rules again. You have strong acids. There are 6 of them. HCl, HI, HBr, not HF, HNO3, HClO4, and H2SO4. And then you're going to have your strong bases. Which are your group 1, CaSrBa, group 2 metals, plus hydroxide. Things that are not going to split are weak acids. So don't split. I hope this is not on the other page. Oh no, it is. Never mind. Okay, moving on. Things that do not dissociate are weak acids, weak bases, insoluble salts, and pure liquids and gases. So like H2O wouldn't split. H2S is a gas that won't split. Okay, so some harder reactions that you might see but are not stressed, so I don't want you to worry too much about it. When you see something that says acidified or basic solution, it's a redox reaction in disguise, which is what we're going to talk about in class in the next couple weeks. Carbonates in a double replacement reaction. So this looks like a simple, straightforward double replacement reaction where you get H combining with your CO3, so you get H2CO3 plus NaF. We would need to balance that, so there'd be a 2 here, 2 here. And so let's just write the net ionic equation. So 2HF, that is a weak acid, so that one stays together. Na2CO3 is soluble, so 2Na plus CO3 2 minus yields. Now H2CO3 is a weak acid, but it's special. When it is in solution, it's automatically going to dissociate into H2O and CO2. So we're going to split this into H2O plus CO2. Plus, NaF will split, so 2Na plus, F minus, 2F minus. So cancel out, and you're left with that. So just be careful about the H2CO3. Okay, indications of a complex ion. We did not talk about complex ions because they're confusing and hopefully not tested this year. They're not tested frequently. Indications of complex ion is when you have something like 2 compounds that have the same anions. So see how you have AgBr, HBr. It's like, what kind of double replacement can I do with that? Well, they don't. They combine. And you would get HAgBr2, but the H is going to be a spectator ion, so that goes away. And then you're just left with AgBr2 minus. So the way you name complex ions, bromine becomes bromo. There are 2 of them, so dibromo. So you name this part first, go back and name the metal, dibromo, silver. And then you need to put the charge. So the way they find the charge is frequently, like normally, you take the number here and you divide by 2 because the charge is normally doubled. So dibromo silver 1 ion. Okay, if you see excess ammonia, that indicates that you also have a complex ion situation. So ammonia, excess ammonia plus CuCl2, they're going to combine. The Cl is missing because it's the spectator. So let's name this one. So we have NH3, when it's in a complex ion, is called an amine. Okay, you have 4 NH3s, so this is tetraamine, copper, and then you need to figure out the charge. So this is going to be a 2. Okay, something else you might see is excess concentrated acid. Like there's one on your homework. Example is Cu plus 2H2SO4 makes CuSO4 plus 2H2O plus SO2. Very weird. I would not worry too much about that either. Okay, and then the last one that's kind of strange is when you have compounds with boron, they usually combine. So BCl3, if you drew it, okay, looks like that. NH3 looks like this. So NH3 is going to donate its electrons. So an electron donor, think the opposite of a proton acceptor. So bases accept protons, so they must donate electrons. So this is a Lewis base. This is a Lewis acid, and then they literally just combine. So you would get B N H H H Cl Cl Cl. Okay, and I believe that is it for topic 4. Later.